All right. All right. All right. So today we have, like we said, exponential function. So by definition, an exponential function is a function of the form f of x equals c times a to the x, where the base a is a positive real number and the base has to be greater than 0 and not equal to 1, and c, which can't equal 0, is a real number. The domain of the exponential function is the set of all real numbers. The base a is the growth factor, and because f of 0 equals c times a to the 0, which is c, it's called the initial value of the exponential function. Okay, so examples of exponential functions, which are below: f of x equals 2 to the x, g of x equals 1/3 to the x plus 5, and h of x equals 2 times 3 to the x minus 3. We notice that for exponential functions, the exponent is a variable and the base is a constant. The base is a number. So these are exponential functions. Okay, so let's go ahead and explore an exponential function, 2 to the x. We want to graph it, then determine its domain, range, and horizontal asymptote. Okay. I'll probably leave that there. Let's see. So I'll come down and I'll rewrite it here. So for f of x, oh my goodness, right. There we go. For f of x equals 2 to the x, we want to go ahead and graph this. So we're going to make an XY chart. Okay. And then I'm going to pick some of the most common values to pick when graphing any type of function. I'm going to go from -3 to 3. You're going to take all of these values and plug them in for x into the exponential function. Okay. So to start with, we have 2 to the -3, which gives me 1/2 cubed, which gives me 1/8. And then 2 to the -2 gives me 1/2 squared, which is 1/4. Two to the -1 gives me 1/2. And 2 to the 0th, anything to the 0th power is 1. And then 2 to the 1st is 2. 2 squared is 4. 2 cubed is 8. Okay. And of course, we want to change these into decimal numbers just to know what they are since we're graphing. And 1/8 is 0.125. And a quarter is a quarter, 0.25, and a half. Okay. So let's go ahead and graph these values. All right. And I could probably stretch these out. Let's see, 0, 1, 2, 3, and then -1, -2, -3. All right. And from my XY chart over there, I have -3, which will give me 0.125, which is just barely above the x-axis. So right around there. -2 is a quarter, not much higher than the last one. -1 is a half. 0 is 1. 1 is 2. 2 gives me 4. And 3 gives me 8. Okay. So here is what our exponential function of 2 to the x looks like. Okay. So we said determine domain and range. Well, from the above definition, the domain of all our exponential functions is going to be all real numbers. And then the range, well, if we look at our exponential function, as x gets smaller and smaller and smaller, so as x gets smaller, y is getting closer and closer and closer to a number. What number is that?
Zero.
Zero. Will we ever touch zero, though?
No.
No. So the range goes from 0, not included, to infinity. And since we'll never touch 0, this means that we have a horizontal asymptote on the x-axis at y equals 0. So we have a horizontal asymptote at y equals 0. Okay. And just to show you that we'll never ever touch 0, we can use Desmos. Why not? So if I type this function in, 2 raised to the x, there we go. There's our graph. And let's go even further down into negatives. Let's say we'll stop at -20. Why not? And if I zoom in, and constantly keep zooming in, maybe -20 wasn't a good one. Too late. I'm already committed. Look at that. At -20, we are still not touching the x-axis. So this would be the same for any negative numbers towards negative infinity. Look at that. Look how small that number is. 9.5 times 10 to the -7. That should basically be 0, but it's not. We are barely above the x-axis right now. Okay. Let me come back to where we were. Yes. All right, we're back. There we go. Whatever that's doing. Okay. Oh, I need to change that. That's weird. 0 to 10. There we go, much better. Okay. So before I move on from this, in your homework, you're going to be given exponential functions with transformations. So I want to touch on that really fast. So let's say that, here we'll call this transformations. Let's say I was given y equals 2 to the x plus 3. What would that plus 3, or actually, better way to say it, what type of transformation is that plus 3? Is that a vertical or horizontal transformation?
Vertical.
That is a vertical. Good. So this would be a vertical shift up by 3 units. If it was a -3, it'd be a vertical shift down. Okay. What if we're given y equals 3 times 2 to the x? What type of transformation is this? Would it be a vertical or horizontal stretch?
Horizontal.
So remember that anything horizontal is going to be combined with the x. Anything vertical is going to be outside the function. So this would be a vertical stretch. Okay, then Now let's say they gave us 2 to the x plus 1. What type of transformation would this be?
Okay, that one's horizontal.
That is a horizontal shift to the left. So x plus 1, we shift to the left. X minus 1, we shift to the right. And then let's say we were given y equals 2 to the 2x.
Same thing.
Well,
Horizontal.
not a shift,
or
but it's a
horizontal
horizontal
stretch.
Well, this one would be a compression.
There you go.
If it was anything between 0 and 1, so let's say if it was 2, I'll write it down, why not? Let's say if it was 2 to the 1/2 x, then that would be a horizontal stretch. Okay. Two more to go. Let's see. If I had y equals -2 to the x, what type of transformation would that be? What does the negative do?
Is that a reflection?
It's a reflection. Reflects over x-axis, which means my last transformation, y equals 2 to the -x, would reflect over what?
Y-axis.
There you go. Boom. So again, the reason I show that is because your homework will have graphing transformations. Just know what they are. And my math lab actually makes graphing them really easy because it'll put up a little input box and it'll say, is it a stretch? Is it a compression? Is it a reflection? It has it all there for you. Nice and easy. Okay, cool. Let's move on. All right, so this big yellow box is just information about exponential functions, as we just saw. The domain is a set of all real numbers, and the range is a set of numbers from 0 to infinity. That's everything that we found there. -infinity to infinity, 0 to infinity. There are no x-intercepts. We don't touch the x-axis at all, but the y-intercept is always at 1. As from the graph there, the y-intercept is 1. Okay. The x-axis is a horizontal asymptote. So we see that from the above. The x-axis y equals 0 is our horizontal asymptote as x approaches -infinity. So like I said, as x got smaller and smaller and smaller, we see that y starts to get closer to 0. Here is some limit notation for you, a little bit of calculus. This says the limit as x approaches -infinity of our exponential function a to the x will equal 0. This means that as x gets smaller and smaller and smaller towards -infinity, we saw y was getting closer and closer and closer to 0, but will never touch. Okay. The exponential function where the base is greater than 1 is an all increasing function, and it's a 1-to-1 function. That's everything on this one. This is all increasing. And if I drew a line through it, a horizontal line, we would only intersect it once, which means it's 1-to-1, which would also mean that if it's 1-to-1, it has a what? What's important about being what's important about being 1-to-1? If you're 1-to-1, you have a
asymptote. What do you call it? The OD.
We learned it last time. Starts with an I. It has a inverse. Inverse. We learned that on 6.2. One-to-one functions are special because they have an inverse. Okay. The graph of our exponential function contains the point 0, 1, 1 in the base, and -1 and 1 over the base. Those are all the points we have. We have those graphed. And the graph is smooth and continuous. See figure 21. Huh? Sure. Okay. All right. Now, let's look at an exponential function whose base is between 0 and 1. So here we have a base of 1/2 raised to the x. So let's go do the same thing. Let's go ahead and graph it, choosing the same exact points. Okay. So just rewrite it. 1/2 to the x. Make my xy chart. And pick my values. -3, -2, -1, 0, 1, 2, 3. Okay. Plug these into the function above, and you'll get 1/2 to the -3, which will give me, if you remember our negative exponent rules, I can flip the fraction inside, and this will become 2 to the 3rd, which will give me 8. So remember that if I have a over b to the -n, then I can rewrite it as b over a to the n. So that's all I did there. And then 1/2 to the -2. Do the same trick here. 2 squared gives me 4. Do the same trick here. You'll just get 2. Anything to the 0th power is 1. 1/2 to the first is 1/2, 1/4, and 1/8. And we know those decimal numbers already. Okay. So let's go ahead and make our graph appropriate again. Zero, 1, 2, 3, -1, -2, -3. Okay. And from my XY chart over there, we said that at 3, we were at 0.125. And then not much higher on the next one, in the middle on 1, 0, 1, -1, 2, -2, 4, -3, 8. And here is our exponential function for 1/2 x. And now this time, as x gets larger and larger and larger, y will start to get closer and closer and closer to 0. But again, will it ever touch?
No.
No. Which means that we have a horizontal asymptote at the x-axis again. Okay. So since this is an exponential function, the domain is still all real numbers. The range is still the same, 0 to infinity, and your horizontal asymptote is at y equals 0. Okay, cool. All right, so what we notice from this one is that now this is an all decreasing function. So this function is all decreasing. It's still a one-to-one function. If I draw a horizontal line through it, I only intersect it once. It still runs through that y-intercept of 0, 1. There are still no x-intercepts. And what? It's a smooth, continuous curve, which is going to be the same information on the next page. All right, but before I go over there, what is another way you can rewrite this function? 1/2 to the x. And when I say rewrite it, I mean exponentially. 1/2 to the x. Could
What are
you
your exponent rules?
exactly? Could you flip that 2 up and give it a negative exponent?
2 to the negative x.
Good. So this would flip up to become 2 to the negative 1 raised to the x, which would give me 2 to the negative x, which means you would have a function with a transformation. What does that negative do in front of the x? What does it do to the graph?
Mirror across the y.
It would make it go across the y-axis. So on the graph that we did above, we did 2 to the x. So all this does, that negative x, is it flips it over and gives us 2 to the negative x. Fun stuff, right? Oh, send me all the way back. Okay, now moving on. Here are the properties of the exponential function where the base is between 0 and 1. Basically what we just did. Domains are real numbers. Ranges from 0 to infinity. No x-intercepts. Y-intercept is 1. This time, your horizontal asymptote is still y equals 0, but as x gets larger towards infinity. It is an all decreasing, it's 1 to 1, and it contains points as -1 and 1 over the base, 0, 1, 1 in the base. Okay. Fun times. So those are properties of your exponential functions. Now let's get into the real fun exponential function, the number e. So e is Euler's number, and it occurs in nature and a bunch of other fun applications. So they use the base of e, or the number e. We use it in business applications. We use it in science applications. So for business applications, you can find the rate that your money's growing at a certain interest rate over amount of time. For science, you can find out how long something's been dead for, right? You can find the age of a dinosaur or just ancient artifacts, which is pretty awesome. What else? What else is cool, Carl?
You can model the absorption rate of medicine and bloodstream using exponential. You can model interest rates on banks. You can model you can use it to model things that, like, you would use trigonometric functions for. So like when you guys do calculus or pre-cal, you're going to learn all about cosines and sines and tangents and all that cool stuff. You can use E to represent that. Man, like so many things. If you understand it well enough, you can get a job being a data scientist and make $100,000 starting a year. Which is all I was doing today. Not making $100,000 a year, but doing a data scientist homework.
You'll get there. You'll get there. Yeah. But it's a really cool, I mean, it's a really cool concept. So it occurs everywhere. I mean, mainly we like to use it for money though, right?
Yeah, I mean, that's how Euler found it. Some other mathematician sent him a whole bunch of like tax documents and was like, hey, I noticed this pattern that's going on here, but I don't know what it is. And Euler, being the absolute genius he was like, oh, it's obviously this, and figured it out in like a month or whatever. And that's why we named it Euler's number.
There you go. So yeah, so it's involved in a bunch of applications. So it's really neat. I definitely recommend you guys to research it. There's a lot that goes on with E. Okay.
And here I am, can't even subtract -4 from 14.
We'll get there, man. We'll get there.
Damn it.
Okay. All right. So the number E is defined as this expression, 1 + 1 over n to the nth as n approaches infinity. So as the number n gets larger and larger and larger, this expression starts to approach the number e, which is a run-on number like pi. It is an irrational number. And I guess it wouldn't be fun unless I showed you, right? We have the time. So I'm going to type this expression into Desmos. Let's see. We have parentheses 1 plus 1 over x raised to the x. And then we are now going to use my table, and I'm going to pick numbers that get infinitely larger. So I'll start with 10, and then I'll start with 100, and then I'll start with 1,000, and then I'll keep going, just increasing the zeros. How many zeros can I have? There we go. There we go. And I'll stop at 10 million. Why not? Okay. Now look at my y values as x gets larger and larger and larger and larger. What is the common decimal number that you guys keep seeing?
They can't really see it. There you go.
There you go. Oh well. Oh, there we go. Perfect. So what's the common number you guys see there? To about 3 places.
2.71.
2.7. Well, I said 3, but fine. 2.718. So as x gets larger and larger and larger towards infinity, you keep seeing this common number pop up, 2.718, 2.718, and the decimals behind it. So e is irrational just like pi. It is run-on decimal numbers. Okay, perfect. So is that anywhere on here? I'll put it right here, which will give us approximately 2.718, and I'll say 2818. 1828. Oh yeah, those repeat after a while. It's pretty cool. Okay. Boom. I'll probably need that up to calculate E now. Okay. So that is the number E. Pretty cool. So now let's actually graph it by using E as an exponential base. So this will be the natural exponential function. So again, we're just going to need to create an XY chart for E to the X. All right. So f of x equals e to the x, and then we're going to do the same thing here. We're going to choose the exact same numbers we've been doing. The most common numbers to pick when graphing: -3, -2, -1, 0, 1, 2, 3. All right. And now I'm going to put in this base. It's going to be e raised to the x. Make my XY chart. And -3, -2, -1, 0, 1, 2, 3. Okay. And I get 0.05, 0.14, and then 0.37. Anything raised to the 0th power is 1. And then we'll get 2.72, 7.39, and 20.08. So I'll say 0.9. Okay. So there's our XY chart for e to the x. Let's go ahead and graph it. Again, I could make my intervals appropriate. 0, 1, 2, 3. -1, -2, -3. Okay. And then from my XY chart, I have -3 and 0.05. Basically, almost touching the x-axis right there. And then negative 2.14, not much higher. And then negative 1 and 0.37, 0, 1. And then 1 and 2.72, somewhere around there. 2 and 7.39. So 3, 4, 5, 6, 7 up there. And then 3 and 20. So that's all the way up there somewhere. So here is the exponential function, e to the x. Okay. We are just like the original function we grabbed today, 2 to the x. We see that as x gets smaller and smaller towards negative infinity, we see that y keeps getting closer and closer to 0. But once again, we will never touch. So here again, we have the horizontal asymptote at y equals 0. Okay. And everything's kind of the same. So our domain is still negative infinity to infinity. My range is still 0 to infinity. And now my horizontal asymptote is still y equals 0. Okay. And that is the number e, guys. So definitely look it up, research it, give it a read. Pretty cool number to work with. Okay. Any questions on this? All right. Ooh. Last page. Okay. So on this page, we are going to solve exponential equations by using the exponential equality property. So what this property says is that if a to the u is equal to a to the v, so if the bases are the same, then you'll set u equal to v and solve for x or y or z or whatever variable they are giving us. But the bases have to be the same on both sides. So let's go ahead and check out number 1. All right. So number 1, you have 3 to the x plus 1 equal to 81. So in order to use that equality property, the bases must be the same, which they are not. So what you want to ask yourself is it possible to make 81 into a base of 3? And if you don't know how to do that, then think of your powers of 3. 3 to the first is 3. 3 to the second is 9. 3 cubed is 27. And what is 3 to the fourth?
$81.
81. Good. So it's possible to make 81 into a base of 3. So we're going to do so. So we're going to get 3 to the fourth. And now we have the same base on both sides. So you will set the exponents equal to each other. So we'll end up with x plus 1 equal to 4. Solve for x, and x equals 3. All right. All good? Okay. Another one. 2. 4 to the 2x minus 1 equal 8 to the x plus 3. Okay, once again, we see that we do not have the same base. So what is a common base that 4 and 8 share?
2.
2. So we can rewrite 4 as 2 squared. But remember, when you rewrite it, it's whatever that exponent you have whatever exponent you have there is going to multiply the original exponent. So this is going to be 2 to the 2 times 2x minus 1 equal to 8, oh, not 8, 2 to the 3rd times x plus 3. Okay. So we have rewritten the bases, and now the bases are the same. So you can set the exponents equal to each other. Okay. So you'll get 2 times 2x minus 1 equal to 3 times x plus 3. Now all we have to do is solve for x. So 4x minus 2 equal to 3x plus 9. Move 3x over, we'll get x. Add 2 over, we will get 11. All right. Everybody good? You want to have some fun, Carl?
Hell yeah.
I have a quick question.
What's that?
Think the bases cancel out, and then we're just solving the exponents. In this
Exactly.
case.
Exactly.
Okay. Got it.
Boom, boom, boom.
But yeah, sign me up.
I'm get you. I got you. Coming at you.
Send it.
Bam. All right. You get the fun ones. Look at those. Ooh, yeah.
All right. Find it real quick. Always takes so long to load.
I know. It's weird.
Let's see. I don't want to give you feedback. That's the last one. Here we go. Let's put that away. Go ahead and share my screen. Okay. All right. So this out of here real quick. Went too far. There we go. Okay. So let's, can I increase it? Nah, it's fine. Let's get a good line size. We'll do this in blue. All right. So we have negative x squared and then x squared over here, and we have e to the negative 3, so just negative 3. Right? And this is what I am thinking about. I know, based off of my exponent rules, that if I have n, well, I don't want to do n. I want to do it like this. My exponent rules say this. If I have x raised to the n raised to the m, that is the same thing as saying x raised to the n times m, right? So this one right here is going to be negative 2x. And then also this one can just be 2x. And then we get good old negative 3. Now, the mechanic behind, or we have, I don't have to show you that because we have this property, right, that says that when our bases are all the same, we get this. So I'm going to use this right here to rewrite my problem. So instead, we'll have e to the negative 2x equals e to the 2x times e to the negative 3. And then right now, I'm going to take advantage of this exponent property that says that if I have x to the n times x to the m, this is equal to x to the n plus m. So then this becomes e to
the first one is x squared. You keep writing it as 2x. E to the negative.
Oh yeah, that will break this one, won't it? Won't it?
Yeah,
Oh yeah.
No,
Okay.
you wouldn't break it. It'd be.
I'd miss a solution.
Oh yeah, you'd miss the solution, but I was like, it wouldn't cancel out the x's, but yeah.
Yeah. But I would miss a solution. Okay, so never mind. We want to leave this as negative x squared. And this will be negative x squared.
You took the derivative, man.
Well, no, you can rewrite it as well, I guess you really can't, but sometimes these rules don't work, I suppose.
You're good.
What's the chat say? We all miss something eventually. Dude, that's me literally constantly. All right. So now we can rewrite this as e to the negative x squared equals e to the 2x minus 3, right? Because plus negative 3 is just minus 3. So then let's us do this as, let's make purple the solving color. That means we can change this to just this. Negative x squared equals 2x minus 3. And we'll solve it like any other quadratic we've been doing this whole semester a million times over. What is this? X plus 3, x minus 1. So then this gives us that x will be equal to negative 3 and 1. You want me to check them?
Nah, you're good.
Yeah. So that is how you do that, guy. Don't get too hasty on taking advantage of these exponent powers because negative 2x squared is technically not raising n to the m like this. It is a very different thing. This is one of those you have to know how to read math correctly. I always make this mistake. I've made this mistake since I was in college algebra. So don't be me. Don't always make this mistake. Remember that it has to have, you have to be able to, have these parentheses around it the right way in order to make it work. But yeah, that's it. Any questions? All right. You want me to do another one?
Sure. It's the last one. You got it.
Okay. All right. So we're going to rely on the same one we used above. This x to the n raised to the m is equal to x in m when we work out this one, right? So we have 4x, which just gives us an x. And then we have, let's see, we can't do the 4s because our lowest power, we always want to try to put it to low. Where is this eraser going? I do not understand what happened. Okay, it's just like not on the screen. I can't see it. Okay, there we go. Oh my gosh. Okay, well, nope, it broke again. Hold on a second. Yeah, maybe if I minimize it and bring it back up, it'll work for me. There we go. Okay. Oh my gosh. Okay, it just doesn't want me to erase things, I guess. Oh, okay. Well, it seems like you're gonna have to take this one anyway, Robert.
All right. Sounds good.
I guess it just doesn't want me to do any.
He's broken.
It's a sign.
It's like, you shall not do this one. All right, cool. All right, where were we? Stuff. Okay, 4 to the x times 2x, 2 to the x squared equals 16 squared. All right. We notice that all of these have a common base of what? Yeah.
2.
2. Good. Oh, man. Now it's freaking out on me. There you go. All right, got it. So that's what we're going to do is change these all into a base of 2. So you'll get 2 to the 2x times 2 to the x squared equal to 2 to the 4th times 2. Okay. And then we see that these have the same base. So like the property Carl wrote, it was x to the m times x to the n gives you x to the m plus n. So for this one, we're going to have 2 to the 2x plus x squared equals 2 to the 8th. And then these bases are the same. So we set the exponents equal to each other. So, and I'll write it with highest power first. I'll get x squared plus 2x equal to 8. Move the 8 over. X squared plus 2x minus 8 equal to 0. And now all we have to do is factor. So this is going to be x plus a number, x minus a number equal to 0. What are the only factors of 8 that can give me a positive 2?
4 and 2.
4 and 2. And here x equals negative 4 and x equals 2. Boom, boom, boom. There we go. All right. Any questions on that page? If not, we are done. Those were exponential functions.